You can think of this video as a sort of week 8 exploration 4. We have one more video about monoids before we move on to the last topic of the course. This video is about transformations between two different monoids, which is another pattern that once you start looking for it, you can find everywhere in programming. So suppose we have two different monoids. I'm going to write these with some generic names like I and F. So F is some unknown monoid operation with neutral element I. Same with J and G. So one of these is on some unknown type A and one of these is on some unknown type B. Now, if we have a function from A to B, which I'll just call foo, we can ask that this function is compatible with these monoid structures. And I'll tell you what this means. Now, remember that a type can have more than one different monoid on it. So for example, the Booleans have and or, among others. So whether a function is compatible or not really depends on which monoid you're talking about, not just on the type signature of foo. So let me tell you exactly what I mean. I am asking for two extra equations to hold involving this function foo. The first is that if you input the neutral element of the first monoid, you will get the neutral element of the second monoid. The second equation is a bit more complicated. If I take two different elements of A, two different values of A, there are two different things that I can do in order to get a value of B, and I'm going to ask that they do the same thing. So the first thing is that I can combine them with using F, using my monoid operation, and then hit it with foo, and then I get a B. Alternatively, I could take my two elements, hit them both individually with foo, and then combine them using my monoid on B. So writing this as an equation, I'm asking for foo of fxy equals g of foo x and foo y. Okay, this is super abstract, but the point here is that if you replace these generic monoids with some actual monoids, you can quite often find situations where these equations are true and you can actually prove them. So let me show you. So here I have set myself up the monoids for list concatenation and for natural numbers with plus. Now I can write the function length, which takes a list and tells you how long it is. This is a fairly straightforward recursive function. I can say inductively x's, then from x's, and then I can say that the length of the empty list is 0, and the length of head const tail is 1 plus the length of tail. So in other words, the successor of the length of tail. Now it turns out that the length function is a transformation from the list monoid with concatenation to the natural numbers monoid with plus. And remember, plus has more than one monoid on it. So for example, we could make a monoid on plus using times with the neutral element is 1. But length is not a transformation for that monoid. It is for the plus monoid. So what this means, my two equations, the first one says that if I take the neutral element of the list monoid, which is the empty list, and I hit it with length, I should get the neutral element of the plus monoid, which is 0. And the length of the empty list really is true, so I can really is 0, so I can prove this by tested. The other equation says that if I take any two lists and I join them together using the monoid operation in lists, which is list concatenation, and then I take the length of it, that should be the same as taking the length of my two lists individually and then joining them together with the monoid operation on the other side, which is plus. So this says that if I take the length of the concatenation of two lists is the sum of the individual lengths. And this is also a really true fact, and I can prove this. I have to do a little bit more to prove this, so I can prove this by x's. And then from x's, Flask handles the base case by itself. This one I can write tested, and I think that will go through. Yes. Okay. So this is a proof of the two equations that say that length is a monoid transformation from the list monoid with concatenation to the natural numbers monoid with plus. Okay, so what else? So think about, for example, map as this type. If I have a function from A to B, then I can lift it to a function from list A's to list B's. F x's x's from x's and then map f empty is empty, and tail goes to f head cons map f tail. So map turns out to be a monoid map for any function at all turns out to be a monoid transformation from this list monoid on A on lists of A to the other list monoid on lists of B. So what does that mean? It means that we need to say that if we take map F for any F and we take the neutral element of the list A monoid, we're going to get the neutral element of the list B monoid, which is also empty. And this is true by tested. And then the other one says that if I take two lists concatenated together, I can map F on both of them individually and then join the results together with concatenation on the other side. So this is an important fact about map. Shall I try to prove this? Actually, I'm not sure how hard this will be. I haven't written this in the script. X's. Let's go by tested. Let's see. Yes. Okay. So these are proofs of the two equations that say that map is a transformation of monoids from one list monoid to a different list monoid. Okay, so there's a lot more examples of this, and I'll get you to play with some of them in the exercises. But there is one more really important example that I want to show you. If we have any monoid, then we have the reduce function. So reduce type monoid A to list A. I say define reduce m x's induct x's, define reduce m x's from m. What have I done? x's. Okay, then reducing the empty list gives the neutral element of the monoid, which is I. And then reducing head cons tail means we combine using F the head with the reduction of tail. Okay, so it turns out that for any monoid at all, reduce of that monoid is a monoid transformation from the list monoid to the monoid that we started with. Now we have to do a little bit of trickery to express this in USC. This is right on the boundary of what USC can handle. So what I'm going to do a little nasty trick. I'm going to set myself up a fake data type like this and a fake monoid where I say, and now I'm going to claim without proof that this fake monoid is actually a monoid. So I'm going to say the neutral element for the left input, neutral element for the right input, and the rebracketing property. I'm going to leave these all unproven. Now, in order to say that reduce is a transformation of monoids, first I will have to say prove reduce make monoid IF of the neutral element of lists, which is empty, is the neutral element of A, of this monoid, which is I. And this is easy, I can do this by tested. The other equation is hard to prove, or much significantly harder to prove. So the other equation says that if I start with something that's the concatenation of two lists, then that is the same as reducing these two lists individually and then joining the results together with the monoid operation, which is F. Okay, so this is a very important fact about reduce, which is not so easy to prove. Okay, so I'm going to start in the usual way. I'm going to say inductively x's. I'm going to line up all of these equations to make it easier to see what's happening. Then I'm going to say from x's. Okay, now ask does handle the base case itself, but something quite interesting is happening in the base case. So I'm going to put the invisible part back in. First, let me tidy up what is generated for me. Yeah. Okay. So in the invisible base case, we have given x's equals empty, prove our equation for empty substituted for x's. So this is prove reduce empty plus y's equals f reduce empty reduce y's. Now, if you look at this, when I say tested, ask will simplify the left-hand side because it knows that empty concatenate y's is y's. And on the right-hand side, it knows that this thing, reduce of empty, is I. So I'm going to say tested where, and then reduce y's. This is the thing it gets from simplifying the left-hand side. And then f, I, y's. I made a mistake. Oh, I missed out a bracket. That goes here. Okay, now, if you look at this thing which we now need to prove, this is an instance for the monoid equations for our fake monoid, because this is saying that applying f with I as the first input is the same as doing nothing. So this is actually a substitution instance of this equation, which means that because I've written this, I've left it unproven, but I have written it. I can finish this goal by saying given. Okay, so all of this was happening automatically. Ask was generating this itself and not showing you. Okay, so that's the base case dealt with. Now onto the inductive step. So here I can say tested and it will simplify this. Now, something a bit strange is happening here because where am I looking? Yes, this thing here, ask could have simplified this more, and it for obscure reasons has chosen not to simplify this as much as it could. This is in fact not a bug, but it's an extremely subtle corner case of ask's intended behavior. So what I can do is I can simplify that more by hand. So this thing I can replace with the simplified version of it, which is f head reduced tail. And when I send this back and say, I want to prove this, not the thing you told me to prove, ask will actually accept that as a valid goal, except I've made a mistake. Ugh. Yeah, indentation, that should be there. Yes, okay. So even though I've changed the thing which ask told me to prove by simplifying one side of the equation by hand, ask still accepts that as a valid goal in this situation to complete the proof. Now, if you look here, the left-hand side of this equation contains something that looks like one side of our inductive hypothesis. So this is like the thing that we're trying to prove, only with x's has been replaced with tail, which is smaller. So what we can do is we can go by root of this thing, but with this part replaced with the right-hand side of the inductive hypothesis. So I can say by root f head, and then the right-hand side of the inductive hypothesis is this thing, but with x's replaced with tail. Okay. Now, this by root has two different subgoals. Ask has handled one of them automatically. If you look at the thing that we're being asked to prove now, this is exactly the fact that substituting the inductive hypothesis into the left-hand side of this equation was actually valid, and we can just do this by under f, because both of these sides have the form f head something, and then the somethings are equal by the inductive hypothesis. So I can say under f here, and at this point we're actually done. Ask has now accepted this proof. It hasn't changed to proven because I'm relying on these fake proofs here, but apart from that, Ask has accepted this proof. I'm going to continue adding invisible things. So this under f, this has an invisible subgoal, which is just the inductive hypothesis, which is given. So I'll leave that. But there's another interesting subgoal of the by root. We need to prove that the thing that we're going by root of is equal to the right-hand side of this equation. So this goes here. So we need to prove that it equals this. And if you look at this thing we now have to prove, this is an instance of the rebracketing equation for our fake monoid with f. This says that combining head, reduce tail, and reduce y's in two different ways using f with the two different bracketings are equal. So this is actually a substitution instance of this equation. So I can get this by given. Okay, and now I really am done. This was a big and difficult proof. Okay, that was the last video about monoids. So in this week's second video, we're going to move on to the last topic for the course.